Good afternoon, everyone. My name is Olli-Pekka Kuusela, and I work as a research fellow here at UNU-WIDER. And I'm very excited to be here presenting our research in collaboration with Alan Finkelstein Shapiro. All right, so let me try to motivate our research using a couple of slides. So as we all know, the frequency and severity of drought events are getting worse, and mainly due to climate change, of course, becoming worse and worse every year as we speak. And this is especially consequential for many countries in the sub-Saharan Africa, impacting their lives of people and their livelihoods. But what was perhaps surprising to me, at least, was also the fact that many of these countries in the sub-Saharan Africa are also very reliant on hydropower for their electricity production purposes. And of course, when you have droughts, that's going to have a big impact on hydro production as well. So you can imagine if there's no water, there's nothing to keep those turbines working in those hydro production facilities. So one country that's especially reliant on hydropower is Zambia. So about 80% of the electricity production in Zambia comes from hydropower. And last year was a particularly bad drought year, and it had huge impacts on their hydro production capabilities as well. So at times, only 10% of the hydro capacity was utilized during the drought periods. And according to some government estimates, the cost of those outages that happened because of the drought and because of the hydro production was not online reached 5% of the GDP. So pretty significant economic costs. So still a little bit more about Zambia. So what we know about the electricity use in the country is that it's very uneven. So large firms, urban areas rely and use electricity. For example, copper mining, we learned a little bit about that in the previous session, is a big consumer of electricity. Whereas in the rural areas, electrification lags behind. So not much access to electricity, at least compared to when you compare it to the rural, urban areas. And because of these electricity shortages and disruptions that have been happening in previous years as well, but especially last year, there's a lot of talk about investing more and more on coal and oil to substitute the unreliable hydro productions. Now, there's also some anecdotal evidence, if you read some news stories of small firms, people trying to switch to using diesel generators to generate electricity when there's no electricity available from the general grid. But of course, not everyone can access and pay for those type of generators. There's also this very important, interesting policy initiative called the Mission 300. So the aim of that mission or initiative is to increase access to electricity in Africa. And in connection to this policy initiative, Zambia's goal is to increase the share of solar power from 3%, which was the share in previous year, in 2024, to 33% by 2030. So there are these two kinds of trends happening right now. So there's this push to install more solar electricity, but there's also this plans to invest also in fossil fuels-based, like coal-based electricity production. So what we are doing in our research, we are wanting to understand kind of the aggregate level impacts of these types of hydropower disruptions. We model them as productivity shocks, and also to understand how these potential subsidies for solar energy producers or installations will impact the distribution of firms, allocation of labor, and macroeconomic outcomes. So what we do, the main methodology, we build a macro model to study the short and long run impacts of these types of disruptions and policies. And in our model, what makes it unique and kind of tailored for this context in Zambia and for sub-Saharan Africa context in more general, is that we have this salaried and self-employed labor modeled in the model. We have firm heterogeneity in terms of electricity adoption. And we have an energy sector where energy producers can choose between 3 different production technologies. So these fossil fuels, hydro, and solar. And our research contributes to this literature on climate policies and macroeconomic outcomes in developing and emerging economies. There's not a lot of research about this yet, but it's gradually expanding and expanding. Okay, so I'm not going to go through the model, equation by equation, because we don't have much time. So I'm hoping that maybe this diagram will give you some idea of how the model works. So we have households supplying labor and capital to the markets. We have energy sector with these three different forms of electricity or energy production. We have urban and rural sectors. In the urban sector, we have self-employed firms, micro-salaried firms, and these small, medium, large salaried firms. In the rural sector, we have self-employed firms. What's distinguishing these firms from each other is the use of input. So not all of them, for example, use capital. So all of them use labor, some of them use energy, and some of them use capital. So that's one distinguishing feature. And then these firms in these two sectors are monopolistically competitive firms, so they have some pricing power, but they then supply their goods to the market, and there's this sort of like a final good aggregation, and the final good is then consumed by the households. And then there's a government in play, but I'll explain government's role in a couple of slides. But what's important as a takeaway from our model is that the choice over the technologies in goods and energy production is endogenous in the model. So it's endogenously. So we don't decide. It's endogenously decided by the model what technologies these different sectors and these energy sectors adopt. A little bit about that adoption, about this endogenous adoption. So we have productivity distribution for these firms. So each firm gets a productivity draw, and based on its productivity draw, it makes a decision what kind of a firm type it adopts, or in the subsequent slide, what kind of energy it adopts. So these thresholds that define whether the firm is going to be a self-employed micro firm or a small and medium large firms are determined in turn by these other factors in the model. So for example, these electricity disruptions will impact how these thresholds move, and as a result impact how many different types of firms we have in the economy. And this is the same picture for the energy production sector. So there we have these three different technologies. And again, these thresholds are endogenously determined, and these firms then choose the technology based on their productivity draw. Okay, what the government does, it finances an exogenous stream of government expenditures and also provides these subsidies for the fixed cost of operation in the energy sector. So what I guess I forgot to mention is that in the previous slide, one critical fact about those thresholds is that there's this fixed cost of adoption as well. So that's an important driver of the adoption decisions. The government collects revenue by taxing these formalized firms, household consumption, and labor income from working in these salaried firms. And the government can also receive these foreign transfers, which we assume go towards these energy subsidies that we study. Okay, so what the calibration and policy experiments, so what we do, we calibrate this model to kind of represent the Zambian experience, the Zambian economy. And after that, we create 4 different scenarios or experiments, as we call them. So there's this first scenario, this permanent productivity shock baseline scenario with 5% GDP loss and about 15% reduction in energy use while keeping the total solar share unchanged. So this is kind of like representing the 2024 experience. Then we do a second scenario where we use the same assumptions in the first one, but we let now solar production also adjust. So there can be investments in solar. And the third and the fourth scenarios are the policy scenarios where the government provides a subsidy to the solar production. So in the first one, there's a subsidy to solar production with the aim of increasing the share of solar from 3 to 33%. So this is the Mission 300 goal. And in the fourth one, we're also allowing the government to subsidize hydro production with the goal of maintaining emissions at the change in emissions at a zero or neutral level. Okay, here are some main results. So again, I'm not going to present all the variable outcomes, just highlighting one of the more important ones. So here in the first column, you can see the first scenario where you have this sort of like energy disruption. You have the 5% decrease in output, as we prescribed. There's decrease in consumption, increase in real price of energy. Total emissions go up by a lot, and this is exactly because of the economy starting to use more fossil fuels. There's increase in self-employed share. There's a decrease in the share of these more formal firms in the economy, these large firms, so that L is signifies the formal, the large firms, or the small, medium, large firms. And then, and then this last row is about transfers, but there's no transfers in this, no subsidies in this first scenario. But if you look at the other scenarios, maybe we can look at the third column where we have the solar subsidy in place. As you can now see, the output is actually increasing, thank you, rather than decreasing compared to the first column. Household consumption is still decreasing even with the subsidy. Energy prices are going up even with the subsidy because essentially this solar is not going to be able to totally replace the hydro shock, the disruption or the loss in the hydro generation. And then we still have an increase in emissions. And this is kind of important, one of the important takeaways. So even with the solar subsidy in place, with this drastic increase in the share of solar, emissions are still going up. And this is still happening because of the economy is tilting towards fossil fuels. So it's getting away from hydro, tilting towards fossil fuels. And this happens even with the subsidy in place. The self-employed share is still increasing, and the share of these large firms is decreasing. And in the last column, we have the policy scenario where also hydro production is being subsidized. So here we can see an increase in output. Consumption is still going down. Energy prices are going up a little bit. Total emissions are at zero, like we have prescribed, so that's an assumption. But now you can see that the impact on self-employment share is pretty much zero. So no impact on self-employment share, and actually there's an increase in the number of these formal firms. So one, I guess, I want to highlight one key mechanism that's driving some of these results, thank you, is the fact that there's this reallocation of capital happening from the hydro sector that's being hit by these disturbances towards the urban sector with these formal work firms in place. So that's kind of like driving also these positive output gains in this model. Okay, so some transitional dynamics we can also generate. I'm not going to go through these in detail, but these are interesting to study later on as well. Okay, so the summary of main findings. So these drought-related disruptions lead to a sharp rise in carbon emissions as energy producers switch to polluting energy technologies. A subsidy to solar energy adoption can more than offset the GDP losses and deliver a long-run fiscal multiplier above 1. However, these subsidies alone, like I already noted, are unable to fully offset all the losses in the economy. So there's reallocation of labor away from the salaried firms and towards self-employment. So that's kind of like a negative development that we get out of the model. And also, like I said, there's this increase in these carbon emissions. Whereas if you have this sort of like joint subsidy for both solar and hydro, that keeps the emissions unchanged. We have a situation that generates substantial increase in GDP and expands the share of salaried firms, keeps the share of self-employment labor virtually unchanged, and delivers a long-run fiscal multiplier below 1. So it's a very costly policy. All right, thank you. That's my brief presentation, and I want to just show quickly a picture of a Kariba Dam from Zambia as well. Okay, thank you.